So there's one last element of groundwater that we need to talk about before we start putting them all together to think about how groundwater moves and why and where, and that's a term called hydraulic head. Hydraulic head. If you were to drill a hole in the ground, it's a long, thin hole. Um, Most likely, eventually, what you'd come to is a place where water would start to rise up inside the well, right? So let's say you're just drilling down, 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 and the water rises up inside the well to this height. So everything down here is water. And the way that hydrogeologists usually refer to where the water starts is they put a triangle on it, like that. So whenever you see a triangle like this over some line, what that's telling you is this is up, this is down, and this is the water line. Okay, and that's what the triangle denotes. All right, so you drill a hole down in the ground and water rises up to some point, and the water is coming in through the bottom here, right? So we would define that the height of the water in the well as the hydraulic head. It's an elevation. It's measured in distance. So distance units, so feet or meters, usually something like that. And it has two components. So imagine that this is sea level down here. So the first part of hydraulic head is this distance, the distance from sea level up to the point in the well where the water comes in. So let's say here in Iowa, let's say it's 900 feet. 900 feet. And that's called the elevation head, or Z. Elevation head. The next part of hydraulic head is the height of the water once it enters the well. And let's say that's 30 feet, who knows. And that's given this unit's psi, the Greek psi. And I'll just say 30 feet here, and that's called the pressure head. So the pressure head is 30, the hydraulic head is 900, and the total hydraulic head, H, which is the total head, H is just the sum of the other two. So in this case, it would be 930 feet. Got it? Pretty straightforward, right? Now, the reason that water moves, and this is something you need to burn into your memory right now, the reason that water moves is because of a gradient in hydraulic head, because between 2 points, the hydraulic head is not the same. And you can, if you've ever taken a class from me, I like to use these analogies. But if you grab a hot frying pan, right? Your body temperature is 98.6. You grab a hot frying pan. The frying pan might be 130 degrees. Does heat move from your body into the hot frying pan, making you colder and the frying pan hotter? Nope. The heat goes from the hot frying pan into your body because nature is always trying to even things out. When you blow up a balloon, the air pressure inside the balloon is greater than the air pressure outside the balloon. So if you let go of the balloon, more air doesn't rush in, air rushes out, right? And so what nature's trying to do is equilibrate or make equal the air pressure inside the balloon and the air pressure outside. Likewise with hydraulic head. If hydraulic head is higher in one place than another, what is water going to do? Water is going to flow from where the hydraulic head is greater to where the hydraulic head is lower until those 2 points are evened out. So groundwater flows from high hydraulic head to low hydraulic head. Always. It's universal. Okay? It's going to flow from high hydraulic head to low hydraulic head. And you already know that the rate at which it's going to flow is at least partially related to the hydraulic conductivity of what it's flowing through. Okay? All right. So let's see. What geologists can do is they can, let's just draw a land surface here. They can, by drilling a whole bunch of wells like this, just observational wells, by drilling a whole bunch of observational wells, I'm just going to put these in here. Let's say that here's a land surface, and each one of these things is an observational well. So somebody just started drilling and noted where the water was at different points. And by doing that, what they found was that you can contour the hydraulic head. In other words, you can figure out where the hydraulic head is, and then you can draw just like topographic contours on a map. And let's say that excuse me, I need to back up half a step. The other thing you need to know is that when you are drilling down from the land surface and you dig a hole and it doesn't fill with water, we refer to that as the unsaturated zone. Unsaturated zone. And the reason it's called the unsaturated zone is because not all of the little pore spaces, the little empty spaces, are filled with water. So that when you dig a hole, the water doesn't necessarily run out of the soil and fill up the hole. It's only when all of the pores are filled with water that when you dig a hole, water runs out of those pores and fills that well. So this is called the unsaturated zone. This is called the saturated zone down here below the triangle. And the triangle rests right at a point, right at a kind of a plane that is referred to as the water table. That's what this point is right here. That's what this arrow will always be sort of bobbing on. It's a water table. Okay, so what I'm going to do over here is I'm going to draw the water table. Like this. And hopefully what you can see, I'll draw a little arrow here, a little triangle to denote that it's the water table. So by drilling these wells, we noted where water first started to enter the well, and we noted that elevation, and so we get the position of the water table. Right? And I think I'll stop right there for now. But anyway, that's an important point.